Today's speaker is Professor Rocco Duvenhage. Rocco obtained his PhD in mathematics from the University of Pretoria in 2002 and is currently a member of staff in the Department of Physics at the University of Pretoria. His research deals mainly with dynamical systems in the framework of operator algebras, as well as the connections to quantum physics. Today, he is joining us to present a seminar entitled Non-commutative Wasserstein metrics. So, Rocco, I'd like to hand over to you. Thank you very much.
Okay. Yes, so I'll talk about what's known as non-commutative Wasserstein metrics. This is a part of optimal transport. It's a classical theory. It's part of probability theory. And I want to show you how one can extend it to operator algebras, first of all. And secondly, in doing it, I would like to show you or give you some idea of what non-commutative analysis is. What do people in von Neumann algebras and C-star algebras, etc. do? So it's two goals. The main goal being the Wasserstein metrics, but the secondary goal just to use it as an illustration of what operator algebras, von Neumann algebras, etc. are about. I'll start with an introduction to the classical work. So optimal transport is a very old problem. It's about 240 years old. Here you see a simple diagram of what it's about. You have some probability distribution indicated here as a heap of material, and the second probability distribution indicated here as some sort of a hole, and you want to fill this hole with the material on this heap. So you can take a little bit of material here and put it there, take a little bit of material here and put it there, etc., until the whole heap has been put into that hole. So it's about taking one probability distribution to another. By the way, there's a cost involved. So for any movement of material from X to Y, there's some cost involved. And the total cost of moving the whole probability distribution to that whole probability distribution is given in terms of an integral of this form, where this omega is a probability measure called a transport plan. The idea is that the probability for such a subset mu Cartesian product V, so a little rectangle, it's viewed as the amount of material in U which ends up in V, where U and V are respectively subsets of X and Y. So in other words, U is some subset here, and V is some subset there in Y. By a transport plan, also called a coupling, we simply mean that the probability measure mu, omega, can be reduced to mu and nu respectively, where mu and nu are the probability distributions that you start off with and end with, respectively. So that's the essential idea behind it. It was obviously not formulated like this 240 years ago, but gradually people made it more rigorous. And that's, roughly speaking, the basic definition of optimal transport. You want to find the transport plan which makes the cost a minimum. And you can see there's some dynamical process in the background. So this is, although not formulated directly as dynamics, there must be some dynamics going from X to Y and from any point to some point there. So in some way, this is a dynamical process, and the transport plan just gives you the end result of this dynamical process. What's interesting is you can use this, cost, the optimal cost, to define a metric on the space of probability measures. So in this case, I'll use the distance squared if I take X and Y to be the same subset in Rn, and I use the distance squared as the cost. So if you compare that C there with this X minus Y norm squared, then I'm using this as the cost. And using such a setup, you can get a metric on the space of probability measures. This is a very special case, but it's a very standard and important case. You can look at much more general costs here and still get a metric. So some metric here squared or to some power p, but I'll focus on the quadratic case. And then this metric W2 is called a Wasserstein metric or quadratic Wasserstein metric. And note it's simply the square root of the total cost for the omega, or we'll see in fact there is always an omega that reaches the infimum. At this stage it's just defined as the infimum, and it essentially is the square root of the minimum cost. These metrics have various applications. They're used a lot in, for example, artificial intelligence. It has applications in physics. So they've become quite useful in modern research, and they have various properties that make them useful. One simple property that I briefly illustrate here is that if you have two probability distributions, this one here and this one here, then the Wasserstein metric between them, the Wasserstein distance between them, will depend on the underlying geometry of the space X. So the further the two probability distributions are from one another, the larger the distance, the value of W2 can be expected to be. So it's a simple property, but properties of those type are what makes the Wasserstein metric so useful. And as I say, it remains an extremely active field, and it even led to two relatively recent Fields medals for Villani and Vigali. Now, of course, I'm aiming to look at the non-commutative case, or a quantum case of this, and I'll work specifically in von Neumann algebras. Now, I'll be using terms like von Neumann algebras, etc. If you don't know what a von Neumann algebra is, I'll try to work around it. So it's not too important that you know the details of all of these things. I'll try to keep the technical material to a minimum and try to carry the idea across, but it's some algebra of operators. That's what you can think of it. So if you know what B of H is, the bounded linear operators on Hilbert space, then a von Neumann algebra is some sort of algebra with involution inside B of H. And non-commutative probability is an extension of usual classical probability that's motivated to a large extent by quantum physics. You essentially replace an algebra of functions with pointwise operations on the space X that we've been discussing by non-commutative algebra, which we'll call A. And in that case, there's no classical space left, so X is gone, but you can still build a probability theory in terms of A, as long as you have sufficient structure. And the structure that we'll focus on here is that of a von Neumann algebra, as I've mentioned. And in fact, the probability theory that one obtains in this process is the general framework for quantum physics. And again, the main point here is that this algebra A need not be commutative. In general, it's non-commutative. And secondly, the points of a classical space X are no longer accessible. But we do have Hilbert space representations of such algebras, and they will play a key role. The recipe, in a sense, to move from the classical to the non-commutative case is that you replace the classical algebra by an algebra A, a non-commutative algebra, and an integral with respect to a measure is replaced by what you call a state on the algebra A. The state is complex valued, linear, so it's a linear functional. It's positive and normalized. The normalization is, as you may expect, due to probability theory. You want the total probability to be equal to 1, and the positivity is related to the fact that probabilities are non-negative, so they lie somewhere in the interval 0, 1. So that's why we have it positive and normalized. And the fact that it's linear is simply because integrals are linear. So it's a fairly direct generalization of the idea of an integral. They're called states due to the fact that in quantum physics, they actually describe physical states of the system. And this is a special case of non-commutative analysis. There are other versions of this. So for example, if you work with C-star algebras, you can view them as a non-commutative topology. And building on these types of ideas, you can obtain non-commutative versions of various classical structures. So I'll focus on probability theory, but keep in mind this is just one example. So operator algebras and non-commutative analysis more generally, you can look at various ideas from usual mathematics, so to speak, and try to get quantum or non-commutative versions of it. The basic idea usually being you have some algebra of complex valued functions on some classical space, and you replace it by non-commutative algebra, usually involutive, so it has some sort of an adjoint. And again, one of the key points is that the points in a classical space are no longer accessible. Now, this is very natural. It's motivated by quantum physics, as I already mentioned, but there are in fact also purely mathematical reasons. So for example, if you take the harmonic dual of a non-abelian group, you don't get a group, you get what's known as a quantum group. And the same ideas that I've just discussed apply there. So there are purely mathematical reasons as well why one wants to study these sorts of things. And secondly, even though you just replace one algebra by another, the phenomena involved are often very non-trivial. So it's not necessarily simple to do this. And it's very interesting, but can often be conceptually and technically difficult. And you'll see some aspects of this as we look at Wasserstein metrics. Now, coming back to optimal transport, let me just give you an idea of what has been done in non-commutative optimal transport. So in a fairly early paper by Bian and Voiculescu looked at Wasserstein metrics in the context of free probability. And they only considered traces. Traces are states of this form that I've discussed previously, where you can essentially commute, roughly speaking, inside the state. So a trace is a special kind of state. It's not quite sufficient for what one would like to do in physics, but it's still a very important example. And they used transport plans to set up the Wasserstein metric. So this paper is reasonably close to the approach that I'm taking in this talk. Another paper that uses transport plans is this one. They actually applied it to physics. They get sensible results, so it appears to be a nice application to physics. But interestingly enough, they don't actually get a metric. So the distance between a state and itself is not zero in this paper, which illustrates that it's not so easy to get a metric in a non-commutative case. But nevertheless, despite that, they made decent progress on certain problems. This is not an exhaustive list, obviously. It's just two papers that appear to me to be fairly important in this field. An alternative approach is via dynamics. So again, if you look at this original sketch that I had here, some dynamical process must be involved to carry material from here to there. And taking that as the basic approach, you can actually set up, both in the classical and in a non-commutative case, a dynamical approach to optimal transport. And in a series of papers, these guys have actually derived metrics using this dynamical approach. They didn't look at the transport plan approach. Classically, these two approaches are essentially equivalent, but as far as I know, that's not yet been established in a non-commutative case. Let's then look at the quadratic cost. So keep in mind, I said we'll look at this cost function, which is just the distance squared. And let's try and see how one would set up a non-commutative version of this. Now, I'll look specifically at the case where this classical set X is a bounded subset of Rn. So these coordinate functions become bounded. And in a non-commutative case, you would replace the coordinate functions by elements from the algebra. Now, this is a von Neumann algebra. Its elements are actually bounded linear operators. And the fact that these operators are bounded correspond to the fact that those functions are bounded if X is a bounded set. A direct translation of the cost of transport, the cost function would then be this, right? So this translates to that. I'm not going to try and go into the details of why that is, but hopefully you can see some correspondence. You have KL in the place of one of the components of X, XL, and a second KL in the second position here in the elementary tensor, which acts as the second coordinate. So it's a coordinate function. Well, it's the second variable, so it's a coordinate function in the second variable y. The absolute value signs here is just to take the square of that. So it's this notation here, the absolute value squared or the mod squared of an element A is A star A. So it's similar to how you would define it in the classical case. So this would be a direct translation of that cost. It turns out that it doesn't work though. So if you try to translate directly, it simply doesn't work. And that's an example of what you have to take account of in non-commutative analysis. Often a very direct translation of the components appearing in the classical case simply doesn't work. Heuristically, an alternative approach is to do this. Now, if you compare to the previous page, I'm looking at the second term, and I'm adding a certain operator called S sub nu. This is an operator that appears in Tomita-Takesaki theory. It turns out to be highly non-trivial, the theory, and I'll discuss the theory in a bit more detail shortly. But if you make this modification, then in fact, it turns out things work out eventually. This is just heuristic. I have to still transform this slightly into a more usable form, but it's a sensible approach that translates this properly, so you get a proper cost function. And secondly, in the classical case, it essentially disappears. So it reduces to the classical case as soon as you apply this to a commutative algebra. So the S just comes up in the non-commutative case. In the commutative case, it essentially becomes trivial. So this is a case in point of non-commutative analysis, as I just said. Instead of using that, we use this. It reduces to the classical case properly. So this construction here essentially reduces to that as soon as the algebra is commutative. This fails to ensure that the distance between the state and itself is 0. That's certainly a minimum requirement for a metric. But if you use this form, you can eventually ensure that you get a metric, and particularly you get the distance between mu and itself being 0. And recall in some previous approaches that wasn't obtained. So this is a key point. One has to set things up properly in order to get a metric. Now it seems like a small change, but in fact it has significant implications and complications, and you'll see some of this as we proceed. This brings us to the algebra versus its commutant. It turns out this construction here is related to the commutant of A. By commutant, I simply mean that you look at A as a subalgebra of B of H, as I mentioned, so it's operators on Hilbert space H, and you look at all the elements of B of H that commute with all the elements of A. That gives you the commutant A prime of A. And it turns out that in a non-commutative case, you have to be very careful about this interplay between A and A prime, because you do need, in some way, the commutant. This element here is, in fact, not quite in a commutant. It's affiliated to the commutant, but as I said, we'll still get this into a more usable form later on, which makes it technically a bit simpler. Now, Tomita-Takesaki theory provides you with anti-star automorphism between A and its commutant. So this is what allows you to move back and fro between these two. By anti-star automorphism, I simply mean that it preserves all the structure of A, all the algebraic structure, but it swaps the product. So AB, if you plug AB into J, you get JB, JA. So it simply swaps the product, but other than that, it preserves the algebraic structure. And again, this form, especially that term there, is the start of making use of the commutant. Now, you may ask, why is the commutant important? So let me try and give you a very simple answer to that. We have our von Neumann algebra. It's some sort of subalgebra on B of H. And I want to try and define a linear map by taking the product of the entries in an elementary tensor. Now, by the universal property of a tensor product, by the way, this sign here is just to emphasize that I'm working with the algebraic tensor product. So there's no completions involved. It's just the algebraic tensor product. And using the universal property of algebraic tensor products, I can extend this to the whole tensor product there. And if I take P of the product of two elementary tensors, then you can clearly see this will give us A, C, B, D. versus if I take the product of the values of P on the two elementary tensors, I get A, B, C, D. So these two are not equal exactly because A doesn't commute. So you would be able to find elements B and C not commuting and causing these two things not to be equal. In other words, P, defined like this, is not a homomorphism. But if we use this instead, so we replace one copy of the algebra by A prime, then C and B are respectively from the algebra and commutant. So C and B commute, these two become equal, and that in fact is a homomorphism. You can even check that it preserves the involution, so it's a star homomorphism. And why this is important is that this has positivity properties. As soon as you have a homomorphism, rather than just a linear map, you have positivity properties, and you can use this to define states, the states that we spoke about earlier. So this is a simple but important point, and it illustrates why we rather use A prime than A in certain places. So in this case, we have two copies of an algebra classically, but in a non-commutative case, we have to replace one copy by its commutant. The second key point of Tomita-Takesaki theory is the so-called modular group. It's essentially a time evolution on the algebra. It's associated with any faithful normal state. I'm not going to look at details of this. Faithful and normal are technical terms. Normal means it's given by a density matrix, so it's physically sound. And faithful roughly means that none of the probabilities appearing in the state is zero. But I'm not going to try and define this in detail, but this is what I'll focus on. But in any case, for such states, any such state, you have a time evolution on the algebra associated with it. And this time evolution becomes trivial in the classical case. So it's simply, as with the commutant, it's something that simply does not appear in the classical case. That's called the modular group. And for our purposes in this talk, it has a significant role to play in obtaining symmetry of the Wasserstein metric. Now, to review Tomita-Takesaki theory very briefly again, we have these two objects, the J that gives us the interplay between the algebra and commutant, and a certain time evolution. Both of these actually emerge from that single operator S that I mentioned earlier that appears in our heuristic cost. And what's surprising is that this S is essentially nothing more than a non-commutative extension of complex conjugation of L2 functions. So classically, if you simply take the pointwise complex conjugation of an L2 function, that's something very simple. There's no problem there. In a non-commutative case, it becomes this operator S. It leads to these highly non-trivial objects, the modular conjugation and the modular group, and a vast theory emerges from this humble starting point. So in a classical case, this theory really doesn't appear at all. In a non-commutative case, it becomes a highly non-trivial and very powerful theory, but its classical starting point, if you will, is essentially just a complex conjugation of L2 functions. So it's a very simple, seemingly simple starting point, which leads to a very non-trivial theory. And again, this illustrates what happens in non-commutative analysis. Something that seems almost trivial in a classical case, in this case then becomes, in a non-commutative case, becomes a very, very non-trivial and powerful theory. And it's essential to do what I want to do in this talk. So it's essentially the core, the technical core, and in some ways the conceptual core of what I'm doing in this talk. So Tomita-Takesaki theory is an extremely important theory, but which becomes essentially trivial in a classical case. Now, Tomita-Takesaki theory leads to what we would call a bimodule. I'll discuss that in a moment. And I just want to motivate it briefly via the triangle inequality. So I'll look at the classical case first. If you have classical probability spaces, X, Y, Z, and you have transport plans between them, then to prove the triangle inequality for the Wasserstein metric, you need, in a sense, a resulting transport plan. You need to be able to compose them. In a classical case, this is called a gluing lemma. And it's fairly straightforward in the classical case, so it takes some work, but you can actually glue them or compose them in a certain way. And hopefully you can see the analogy. You either go from mu to xi directly or via nu. And that's exactly what you have in a triangle inequality. You go from one point to another directly or via a point that's somehow in between. And from that, you get the triangle inequality. Now, in a non-commutative case, we need an analogy of this. So we need some sort of non-commutative analogy of this gluing process. And it turns out the theory of bimodules in a sense of Kohn, which fits in exactly with Tomita-Takesaki theory, is an excellent way of doing this. Now, bimodule in this case is a Hilbert space with a left action and a right action of a von Neumann algebra. So you have some algebra, von Neumann algebra A, acting from the left, and a second von Neumann algebra B acting from the right. And schematically given this setup of von Neumann algebra with state, a transport plan, which I'll still define in more detail later on, transport plan to a second von Neumann algebra state to a third, we need to compose those two transport plans, which I schematically indicate here. But more than that, we also need to glue corresponding Hilbert spaces. And again, I'll get to the details of this later on. But this gluing is given by what's known as a relative tensor product. So if you have a bimodule H, a bimodule K, and B is in the middle, so it acts from the left on A, from the right on H and from the left on K, then you can take what's known as relative tensor product to get another bimodule. Now, the composition of the transport plans you can still do without bimodules, but to prove the triangle inequality completely, you actually do need this bimodule structure. And again, this relative tensor product is a highly non-trivial construction in von Neumann algebras, which I won't go into any detail, but roughly speaking, it's a tensor product of H and K over nu. So in a sense, it absorbs some information, and I'll show some diagrams later on which will hopefully help clarify it. But in any case, the basic path is we need Tomita-Takesaki theory. This leads to bimodules, and these bimodules in turn are exactly the tool that we'll use to prove the triangle inequality. So let me get to our technical development more directly. So I have to define what's meant by transport plan in a non-commutative case. I'll look at two von Neumann algebras A and B. I use the commutant of the second, so this is in line with what I discussed earlier on. And I look at a state on this algebraic tensor product, omega, and it has to reduce to the initial states that I start off with mu and nu. So this is a translation of the transport plans in the classical case that I showed earlier. And this is the definition that we'll use. And again, note the fact that I have to use the commutant. So again, this illustrates that you have to bring in ideas that do not appear in the classical case at all. So that's our basic definition for transport plan. And again, if I don't use the commutant, I run into problems like this. The distance between mu and itself is generally not zero. But if I do use the commutant, then this problem is avoided. Technically, we actually need a slightly smaller set of transport plans defined in this way. I'm not going to try and explain this in any technical detail. I just want to show you that the modular group is involved. So instead of using a general transport plan, we'll use what's known as a modular transport plan. In the classical case, they're equivalent. The modular group becomes trivial. So classically, these two cannot be distinguished. But in the non-commutative case, it seems to be essential to use these modular transport plans, a slightly smaller set of transport plans in the non-commutative case, in order to get symmetry. So if we want to get symmetry of the Wasserstein metric, we want to prove that it's symmetric, then it seems necessary to do this. This property here is what's known as a balance property. It's something I worked on with a PhD student, Michiel Snyman, a few years ago. And it's now being used in Wasserstein metrics. Another ingredient that we need are unital completely positive maps. I'm not going to define them in complete detail, but it's a map with a special type of positivity from one von Neumann algebra to another that you can associate with transport plans. So for every transport plan from state mu to state nu, you actually have a UCP map from A to B, such that this a condition holds. And in quantum physics, these are actually quantum channels. So these unital completely positive maps are quantum channels. They're generalized forms of dynamics. So this corresponds to our idea at the beginning that the transport plan is some sort of dynamical process. And here you start to see it in the quantum case. The transport plan can be associated with a UCP map, and that is physically a quantum channel. Given this idea of a UCP map, we can then define the composition of two transport plans. You can associate a transport plan, you can associate a UCP map with each of the two transport plans. You compose the two UCP maps, and that then in effect defines the composed transport plan. So this is a nice way of defining part of the gluing process that I mentioned earlier that we need. So we view it dynamically in terms of a quantum channel. And I'll often denote this composition by phi. Now I mentioned earlier that Hilbert space representations will play a key role. Partly this is because I'm looking at a quadratic case. And it turns out that for each transport plan, omega, you can associate a so-called cyclic representation. So if this is a transport plan from mu to nu, you have a cyclic representation, which I will not define in any detail, but it's a Hilbert space representation of the algebra A, tensor B prime, and you can get cyclic representations of the original A and B with the states mu and nu from the cyclic representation of the transport plan. So if you have a transport plan from mu to nu, then the corresponding representation associated to the transport plan gives you representations of the original states. Now let me come back to the cost of transport, and I'll connect it to this representation machinery in a moment. From now on, I'll focus on the case where the algebras involved in the triangle inequality are actually equal. This is, of course, what we eventually want, but I'll still sometimes refer to them as A, B, and C just to show you where we are in this setup, right? As we move closer to the triangle inequality. So I'll take A, B, and C to be the same on my algebra. I still want to make this heuristic plan reality. It has to give a cost via omega applied to C. This is simply an analogy of the classical total cost. And in terms of the representations that we just discussed, we can actually make this definition of cost more precise in terms of representations. It takes a bit of work to see that this is the correct definition, so I won't do that. I'm just showing this to you to give you an idea of what is done more precisely. So you don't need to understand the details of this, but the representation machinery that we set up is a way to make the total cost rigorous. And you can write in slightly different forms, but note that it depends heavily on the Hilbert space representations that we're using at the moment. And that then leads to the main definition of the stroke. We can define a Wasserstein distance. I'll call it a distance for the moment, just to distinguish it from a metric. So I still need to prove that it's a metric, so I'll just call it a distance to distinguish. But you define it as the infimum of the square root of that cost, which we just defined there. And this will then eventually be our metric. We still have to prove it. We have to prove the triangle inequality. We have to prove symmetry. And we have to prove that the distance between mu and nu is 0, if and only if mu and nu are equal. So I'll focus more on the triangle inequality, but hopefully I'll have time to briefly show you what happens to symmetry. But this is our main definition. And keep in mind, a lot of machinery is already built in. We have the algebra, it's commutant. We have representation theory, etc. So a lot of Tomita-Takesaki theory is essentially already built in here. You see, for example, that it's the modular transport plans. So a lot of Tomita-Takesaki theory is built into this definition. Now, if you have the representations, then this is how we obtain bimodules. So by bimodule, again, you want to multiply from the left and the right. So if you're thinking of an AB bimodule, then you want to be able to multiply with an element of A from the left, element from B from the right. And these representations that we get from a transport plan actually allows you to define that. And the definition is given by this. And you'll see the modular conjugation, that J, appearing there. And recall that it takes an element from the algebra to its commutant. And the fact that elements from A and A prime commute is exactly what makes this a bimodule. So again, I won't try and fill in any technical details here, but the key point is from Tomita-Takesaki theory, you can actually define bimodules using the representations that we've set up. And then again, just to remind you, if we have two transport plans, we can take the relative tensor product of the resulting Hilbert space representations. So if we put the last few slides in a more diagrammatic form, we have representations for our states mu and nu, as well as I. If we have a transport plan from mu to nu, we have a Hilbert space representation of that. Similarly, for the second transport plan. And those transport plans, of course, are in some way, the Hilbert spaces associated with those transport plans are in some way embedded into this relative tensor product. So this diagram just gives you a summary of all of the representations as well as the relative tensor products, in other words, this bimodule idea. But you'll note that it's not connected. So we still need to show that these things are connected in some way. And that's part of what we need for the triangle inequality. So let me get to this in a bit more detail. We want to prove the triangle inequality for our proposed Wasserstein distance. We have bimodules involved. We have relative tensor products involved. And this relative tensor product is going to be the space that we'll use to prove the triangle inequality. And roughly speaking, so very schematically, if I take the tensor product, the relative tensor product of the two Hilbert spaces associated with the two transport plans, and keep in mind again, the transport plan goes from mu to nu to xi, so the idea is that we want to get the triangle inequality from that. If I take this relative tensor product, then it actually does connect up those diagrams in the previous slide. It tells us that if something is here in the middle, then I can go via either of the two transport plans and end up in the same place in H. This is the main property of the relative tensor product that we'll use, and this is exactly what we need to prove the triangle inequality. If I make these pictures a bit more precise, then you get a lemma of this sort. I won't discuss this in detail. It's just the expression of that diagram in an algebraic form. Our composed transport plan also, of course, has a Hilbert space associated with that. So remember, phi is the composition of the two transport plans. That in itself is embedded in the relative tensor product, but this space by itself is simply not sufficient to prove the triangle inequality. We really do need the relative tensor product. So let's get to the triangle inequality. This is what I would like to prove. And the main step in that proof is displayed here. And what I would like you to notice is simply that the relative tensor product, H, is exactly what is being used to prove the triangle inequality. And this middle term here is 0 exactly because of this diagram. That middle term corresponds to H nu, and you can go in two directions ending in the same place. So the difference here, the norm of that difference, is indeed 0. So by using the bimodule and the relative tensor product, I can indeed make this middle term be 0, which is what gives me the main step in proving a triangle inequality. And at this moment, I'm not aware of another way of doing this. So it seems the bimodule approach, along with the relative tensor product, is not just natural, but it's possibly the only way. I don't know that it's the only way, but it may very well be the only way of doing it. at least in the setup that I've used so far, using the definitions that I've set up. So, but at the very least, all of this machinery is a very natural way of proving the triangle inequality. So again, just to remind you, we connect everything up with the relative tensor product. This allows us to prove the triangle inequality for our Wasserstein distance in the relative tensor product by making this term in the middle disappear. So that's one of the key points in my talk. Let me look at symmetry very briefly. One defines, we defined the modular transport plans, and using those along with what's known as a CoE-MaSS dual, which I'm not going to discuss in any detail, it's a non-trivial idea, but using that, one can ultimately prove that you have symmetry. And it uses this CoE-MaSS dual via lemma that I've shown here, which requires a bit of work to prove, but it's not too difficult. Secondly, well, the remaining point that we want to show is that this is 0, of course, and then secondly, if you have the metric or the distance between mu and nu being 0, then mu and nu should necessarily be equal. And again, using some ideas from Tomita-Takesaki theory and a number of other techniques from von Neumann algebras, one can go through a few lemmas. Now, the one lemma is displayed here. Again, I won't try and discuss it in any detail, but it does say that the distance is always reached, so that infimum is actually a minimum. So this lemma is part of the proof of being a metric, but it does have independent interest. It says that the infimum is always reached, so there always is actually a minimum transport plan. It exists. You don't just need to approach it, you can actually reach it. Secondly, we have a lemma that involves these k's, and it tells us that in order to get a metric, these k's have to generate A. This is similar to what we had in the classical case. We have coordinates in Rn. They, in a sense, generate the whole of Rn. And an analogy of that is then necessarily also in the non-commutative case. You cannot get a metric if these k's do not generate the algebra. And this corollary just makes it a bit more precise. If the cost is 0, then there's only one transport plan that achieves it, and that transport plan implies that the two states involved are in fact equal. And that then proves the whole theorem. So the end result is that W2, as we defined earlier, is indeed a metric. If A is not generated by these elements, you can give examples where it's not a metric anymore, it's only a pseudometric. But with that assumption, it is a metric. And keep in mind, all the machinery that was involved, especially the bimodule and Tomita-Takesaki theory, to prove the triangle inequality. That's the part that seems to sometimes go wrong in other approaches. But using these tools correctly then leads to a metric. The technical details you can find in this paper that I put on archive. It will appear in Journal of Operator Theory. But all of the technical details that I left out, which is the majority of the technical details, can be found in that paper. Okay, thanks very much.
I'm just wondering, Rocco, if you looked at or considered if this Wasserstein metric approach can be used to model a normal W-star dynamical system. Perhaps it could be results along the lines of the evolutionist in direction of minimum cost.
Well, I want to study the connections to dynamics further. So this is the main reason why I'm looking at this, but I haven't looked at it in a lot of detail yet. So I think the main point would be to look at things that we've looked at before, namely equilibrium versus non-equilibrium, and to see if a distance between states becoming bigger, so this Wasserstein metric becoming bigger, can relate, for example, to a system being less and less in equilibrium. So I'm hoping that it will be a refinement of the balance ideas that we studied previously. Okay. So this is Michiel, this is the student I mentioned that worked with me on the balance ideas. I mentioned him earlier. So we worked on balance, and I'm hoping that these Wasserstein metrics can help us refine the work that we did in terms of balance before, related to equilibrium versus non-equilibrium. But the specific question that you answer that you ask, I cannot answer at the moment.
It looked like I'm not sure, but it looked like the transport plans can be used to get unital completely positive dynamics, perhaps.
Yes, yeah, definitely. But the question is, what are all the implications of that, which I simply don't know at the moment.
Okay. No, thank you.
Thank you very much for the opportunity. Rocco, also thank you for this very clear and interesting presentation. I can maybe just say Rocco was a student of mine and did his PhD with me. Rocco, I just want to hear. I mean, it's really interesting, and it's actually fascinating to see how one can actually use Tomita-Takesaki and Alan Korn's work to get to these definitions and then hence prove the metric property. But what I want to actually ask you is what is the actual? I mean, I'm particularly not familiar with these transport metrics. What is the sort of idea or the end idea that you see you would like to apply this to in terms of getting? And I know you've mentioned the equilibrium states and so forth, but is there something beyond this that one would actually get some new sort of interesting results in dynamical systems theory, or what?
Well, I hope so. Yeah, I hope so. So as I told Michiel, I'm not sure yet what it will lead to, but my previous work related to ergodic theory, so work that we did together, for example, in particular joinings, and then the work I did with Michiel on balance, they all relate to this very directly. So the transport plans are actually just joinings. They are identical to what I used in my previous work in ergodic theory, and they're exactly the same objects that appear in my work with balance on balance with Michiel. So the starting point of these things are all the same. They're exactly the same ingredients, but just doing different things with them. And a problem that me and Michiel wondered about was exactly how to make balance more quantitative. So we spoke about things, or we discussed things, or we treated things, that systems that are in balance or not, or that may be more or less in balance. And the balance reflects a certain common structure in the two systems. So if system A and system B are in balance, then it reflects some sort of common dynamical structure inside them. And we would like to know how far or how close those two systems are. So this is related to, for example, in joinings, to the idea of being disjoint or not. If two systems are disjoint, they're considered to be very far from one another in the sense they don't have any common structure. And on the opposite side, they can be equal. So we have the range from being equal to being disjoint, but it's not at all quantitative. It's simply qualitative. So my hope is that one can take the qualitative ideas that I had in my previous work. So this is my work in ergodic theory on joinings and the work that I did with Michiel on balance, and make it quantitative. So that's the overall goal. But at the moment, I don't yet know exactly how to do that. But with these metrics, I hope that one can make progress on that.
Thank you.